All right, so we're going to go through the basics of free fall. So, what does it mean if an object is falling freely? That means that the object is only under the influence of gravity. And I hope that you get speed watch this so you don't have to watch me write different things. Similarly, another way to look at the definition of free fall that it is only being affected, I'm sorry, if it's only under the influence of the force of gravity, then there's no air resistance involved at all. So, no air resistance. So basically, you have an object that's moving through the air, and all you have is the force of gravity dragging it back down to the earth. So the variable that's used for the quantity for free fall acceleration. So typically, we use acceleration for most linear motion, but when we talk about gravitational acceleration, we use the lowercase g to stand for gravitational acceleration. The magnitude of gravitational acceleration on the planet Earth is 9.8 meters per second, which means that that is the amount the speed changes every second. Every second, that speed increases by 9.8 meters every second. Now, in the AP world, it is totally okay to round this number off and say 10. And in fact, anytime that you have any kind of mathematical calculation, unless you're told otherwise, you can always use 10. And the direction for the acceleration is always going to be down. So always directed down. Now, this means when you set up your coordinate system from which we make all measurements, you have to decide which direction is positive or negative. So typically, if this is the ground level, um, anything that is in this direction is typically treated as the positive direction, and anything that is kind of moving towards the ground from above is treated as the negative direction. There are some instances where we might make down positive, but for most cases, we're going to make the downward direction negative. But again, this is a choice. This is kind of user defined, but we know that the gravitational acceleration is always directed down.
All right, and now we'll go through the direction of the motion map. So we're looking at a velocity motion map and an acceleration motion map. So if this is where my object starts, and let's say that it starts from rest, release from rest, and just dropped, as it moves downward, that speed is going to steadily increase by 9.8 meters per second squared every second. I'm kind of running out of room here, but I'll just kind of keep going there. So that would be a good indication of the velocity vectors. Now, if I want to draw pictures of the acceleration vectors, so I'm just going to make a separate column here. The acceleration is constant and it is always changing at 9.8 meters per second. So if I draw the same dots to represent the motion, the acceleration vectors would be a constant length showing 10 meters per second down. And I'm going to kind of draw it off to the side here because otherwise they kind of flop on top of each other. And I'm going to try to make them all the same length. And this is showing all the same constant acceleration. So again, speed is zero. So even here where the speed is zero, I'm still accelerating, just like the cart going up and down the ramp from a couple of lessons ago. All right, so this is also kind of a repeat of what we've done before. So envision this as just like if I take a ball and I throw it up into the air, the object slows down to the top where its speed is equal to zero at the top, and then it speeds back up as it's coming back down the other way. So slowing down, speeding up. So if we treat the upward direction as the positive direction, if we start our position time graph at position x equals zero, so we'll say initial position is equal to zero right here at this level where he releases the ball, I'm going to slow down to the top so we see a decreasing positive slope, and then I'm going to start speeding up on the way back down. So increasing negative slope because now it's coming back down the other way. The velocity versus time graph starts with an initial positive velocity, slows down to zero at the top, and then continues to speed up but now it's coming back the other way in the negative direction. In fact, if I kind of flip this color here, this dotted line here is going to represent the same instant in time. I'll extend that all the way down to acceleration. And then finally, if we look at the slope of our velocity time graph, which is constant the entire way, we see a constant negative acceleration. In fact, that value would be minus 10 meters per second squared. So these are the position, velocity, and acceleration graphs. They are identical to a cart going up and down the ramp. It's just we don't have a ramp now. We just have throwing something up in the air and coming back down. All right, I wanted to do dive in a little bit more detail with this ball being thrown up the air, and we can see the positions of the ball at different locations, and just talk about some of the conceptual things that we can get from this. So, just as an example, I'm going to say that this person throws the ball up with a speed of 40 meters per second just to start. So, as it is released from its hand, again, we're not talking about the actual throwing motion where you wind it up and you throw. We're talking about the moment it least reaches, leaves the hand. So 40 meters per second up. We know that the speed decreases by 10 meters per second every second. So if we take these dot right here as being 1 second later, then my speed will have gone down to 30 meters per second right here. And then at time t equals 2 seconds, it's going to be equal to 20 meters per second. I'm running out of space here. Right there, here, after 3 seconds, it'll be 10 meters per second. And then finally at the top, you're going to have your speed equal to 0. So we see an example here where our speed is decreasing by tens every second on the way up. Now, on the way back down, we still have that same constant acceleration. So 1 second later, at this point, we're talking t equals 5 seconds. My speed is now going to be increased by 10 meters per second. So now it'll be 10 meters per second, but it's directed down. So I'm going to put that negative sign there. T equals 6 seconds. It's going to be minus 20 meters per second. T equals, and we'll make it 20 here. T equals 7 seconds. It'll be minus 30 meters per second is my speed. And then finally, when it gets back down to the same position that it started again, in the absence of air resistance, this is t equal 8 seconds, the speed is going to be equal to minus 40 meters per second. So a couple of conceptual things that you see here. In the absence of air resistance, if an object is in free fall, if it has the same initial and final position, so our final position here is going to be equal to 0, with our initial position here also equal to position 0, it's back exactly where it started. As long as it has the same displacement, it's going to have the same speed, just in the opposite direction, up as opposed to down. So here, if we look at the displacement at 1 second, the displacement at 1 second is the distance here. I'm not going to go through and calculate it right now, but it's the same displacement at 7 seconds because it's at that same location in space. Just remember, the displacement doesn't care that it went up and came back down again. It's just final minus initial. So we see some symmetry here that we want to take advantage of in our problem solving. The other thing I wanted to point out again and to remind you that even here where the speed is 0, just for an instant, that acceleration is still going to be equal to g, and it is still going to be equal to minus 10 meters per second squared. I guess in this context, my minus is indicating that it is directed down. All right, so just some tips if we're doing some numerical problem solving. You want to make sure you set your origin, meaning your initial position is where you start the object. Make sure you label it on your graph. Sometimes I typically say wherever I'm going to make my time t equals 0, that's where I want to put my position equal to 0. So we make sure that we put that in there. Label that initial position, set your direction, label it on the sketch. Again, we have the up and down. We want to make sure that we're consistent, just don't change it. Typically we make up positive and down negative. But in certain cases where all that is happening, if somebody is just dropping something at a speed like the diagram that we had seen before, if everything is directed down, so it is the speed is directed down, the acceleration is directed down, and in fact, the displacement is directed downward too. Instead of making all of these negative, you can make them all positive as long as it's not changing direction coming back up again. But this is the only case where you might want to make down positive, but you don't have to. If you want to make down negative all the time, you just make sure everything is directed down and everything is negative. Okay, so about setting the direction there, identify givens that, and especially ones that you have to infer. So remember at the top of a trajectory, when something is thrown up in the air, that speed is going to be equal to 0, and g is always equal to 9.8 meters per second down, but we of course can approximate that and use 10 meters per second, again, down. Look for symmetry because that might be an advantage. We talked about that on the previous slide. All right, so this problem, I'm going to get you started with listing out the givens and the unknown and the unknowns for each one of them, but I do want you to give it a try on your own and then come back later and look for the solution, which I will post or we will discuss it in class a little bit later, but definitely give it a try as you start. So a rock is tossed straight up and then it falls down a 10-meter hole. So just as a quick sketch of what's going on here, here's my ground level, and I'm going to call this my initial position equal to 0. The rock goes straight up in the air and then it's coming down a hole, right, like that. So I'm going to say this location right here is equal to minus 10 meters. I'm going to make the downward direction my negative direction, and that's what's basically happening here. What else do I know? Well, when it gets all the way to the top, we know that the speed at the top is going to be equal to 0. And we also know that my acceleration, which is going to be equal to g, is equal to 10 meters per second squared down, and I'm going to label down as negative, so I'm put the negative sign there. All right, so now we want to go to how high will it go? Well, I want to figure out how high it will go. I'm looking for this change in position right there. That's how high it is going to go. And let's say relative to where it started, because that should actually be in there as part of the question, to where it started. And I will fix that in future years. So again, list our givens. We know our initial position is equal to 0. How high will it go is what we're being asked to find. We know our acceleration is minus 10 meters per second squared. We know that the speed at that point of how high it will go is going to be equal to 0 meters per second. Again, that'll be our final velocity for just that bit. And I think we don't know the time. So that kind of tells us that t is the missing variable. We're not asked about it. It's not a part of the given, so that's the missing variable that's going to help you decide which equation to use. So hopefully that's enough of a hint to kind of get you started. Okay, the second question is almost like a reset button. Now we're looking at a different part of the motion. So we want the object's velocity as it hits the ground. So now I know my initial position is equal to 0. My final position is going to be the ground, which is going to be minus 10 meters. Once again, I know my acceleration is equal to g, which is equal to minus 10 meters per second squared. And I want to find that final velocity, which is equal to my question mark. And again, I still know my initial velocity is equal to plus 28 meters per second. And I probably should have included that over here too. My initial velocity is equal to 28 meters per second. All right, so once again, time is missing. We don't care about it. We're not asked about it. So it's kind of giving us a hint as to what the missing variable is. We want to solve for the final velocity. And then finally, we care about the time. And we want the total time that it takes to complete its trajectory, which really refers to this other question here, which was the whole up and the down problem. So hopefully this is enough to get you started. And for the last part, go ahead and give it a try.
Hey, and don't forget, there's a part D on the next page, so make sure that you finish that as well.